In this class, we will look at a preview of beam analysis to start with, and then look at shell analysis to look at the parallels between them. And both of these would be based on the variational asymptotic method. And beam, we will be talking about it. In the end of last class, I showed you a slide on the kinematics of beams. So here we will try to look at the details of that kinematics, because that plays a very critical role in the development using RAM. So the development of the kinematics itself has actually nothing directly to do with RAM, but it enables the application of RAM and eventually dimensional reduction. And this kinematics is geometrically exact because the geometry of curves, in the case of beam reference lines or curves, and the geometry of surfaces is pretty well understood for a long time, even before people started modeling beams or any structures for that matter. So that's basically what we incorporate, but of course we introduce terminology in our own way, which will be kind of convenient for eventually applying the variational asymptotic method to all these problems. So this is where we left in the previous class. So as I said, we start with a beam over here, and this beam we basically represent in the form of a reference curve, which we denote by small r. And as I mentioned in the previous class, we will use small letters, small or lowercase letters for all the undeformed configuration variables, and for the deformed configuration variables we will typically use uppercase, with a few exceptions of course that I'll come to later. But basically we are representing the beam diagrammatically in the form of a reference curve and a reference cross section. So it will have of course cross sections throughout its reference curve. We are not basically showing that in this particular diagram. And of course, as we said, it can be as complicated a beam as you can have, in the sense that this cross section need not be the same everywhere because of taper and many other reasons. For example, in the case of a wing, the change of the airfoil cross section and so on and so forth, or sweep angles and so on and so forth. And of course, an initial curvature is demonstrated here. Similarly, you could have initial twist as well. Now, for this reference curve, it intersects the reference cross section at a particular point. Now, we denote the position vector of that point from a known reference frame A. Unlike many other developments, there is no necessity that this reference frame A, which is the base, that it be inertial. So it can be non-inertial as well. The only thing that we require is that its velocity and angular velocity, that's the reference frame of course behaves like a rigid body as any other reference frame would. So it has a certain velocity and an angular velocity that should be known for all time for which this particular beam problem is being solved. Now this really helps because, especially keeping in mind that we are going to apply the developments to vehicular structures, in particular aircraft and or helicopter structures, you know that the beams that we are looking at are either the wings and or the rotor blades. Now these are part of a much bigger system, which is the vehicular system. In the case of a helicopter, of course, it's a part of a rotor, which in turn is a part of the helicopter. And so basically, the reference frame to which it is basically connected is also moving. So we are not interested in dealing with the vehicular dynamics at this point of time. But because of the modular fashion in which we are developing this, and this requirement that this need not be an inertial reference frame, makes it convenient because we can, once this development is finished, the results can then be used as a module with vehicular flight dynamic analysis, and then the whole thing can be coupled and full analysis for the vehicle as a whole can be done, and with the components, namely the wings and our rotors, being fully flexible and allowing for all kinds of deformations. So let me see if you can name that. I think a little bit is getting cut. We will introduce some of the variables that we have over here. The variables one by one. First of all along the reference curve in the undeformed state, namely lowercase r, we have the coordinate x1. So typically it can go from x1 equal to 0 at one end to x1 equal to L at the other end. Where of course for a statics problem we require that L should be much larger in dimension compared to the cross-sectional dimensions. And in the case of dynamics problem, the wavelength, which can be equal to or smaller than L, has to basically be larger compared to the cross-sectional dimensions. Next, we introduce unit vectors v1, v2 and v3, v1 being tangential to the reference curve everywhere. So which means that for an initially curved reference curve as is shown here, v1 can change with x1. In other words, v subscript 1 will be a function of x1 in general because of the initial curvature. On the cross-sectional surface itself, which is a plane, we introduce two mutually orthogonal vectors, v2 and v3, so that v1, v2 and v3 will form an orthogonal textural triad. And so you see that v1 cross v2 will be equal to v3, so that's basically what it means by textual, otherwise it would have been minus v3. So you have the right hand thumb rule to see that when you go from v1 to v2, you basically come out with respect to v3. So that's basically the system that we introduce. So the way v2 and v3 are introduced within the cross section, of course they have to be perpendicular to v1 mutually. But in addition, you can have a rotation about it according to your convenience. So for a rectangular cross section, for example, you can take it parallel to the width and the thickness for convenience. But in some other examples, maybe the principal axis might be more suitable. So we have full freedom in the sense of the actual choice of v2 and v3 within the cross section, as long as they are perpendicular to each other. So now we introduce position vector small r, because it's undeformed state. Again, this is also small, lowercase. So you're starting from the reference frame A, point fixed in the reference frame A, and basically drawing the vector up to the intersection of the reference curve with the reference cross section, and that vector will be denoted by R. Now you take any other arbitrary material point, including possibly this, but not necessarily on the periphery as is shown here. It could be anywhere in the interior as well. And you form that position vector from the same point in A as r hat. Okay, again lowercase. So the hatted quantity basically refers to a general point anywhere in the cross section, whereas the unhatted quantity refers to the point which is common to both the reference curve as well as the reference cross section. Next, we introduce the deformed cross section. So again, here it is the blue shade, which basically is the final configuration at a particular point of time. At different points of time, of course, this can change. We're just looking at one particular point of time. So at that point of time, it is the green surface, which was a plane, has now become a blue surface. In general, it could be non-planar. Now we introduce intermediate surface, which is a plane, which is basically that orange thing that you see there, and that we basically say is the average of this blue thing. In other words, the motions of all the material points from this undeformed state to the deformed state, if you average it out, it's basically that. In other words, if, for example, this were a rigid body, it would move and it would have 3 translations and 3 rotations, as any rigid body can have. And that is basically what this is. In addition to that, the cross section can change its shape and size, which is basically what has resulted in the blue thing. So the difference between the blue and the orange is basically the warping. So, and by warping we mean the 3-dimensional field. So it basically means that the plane section no longer remains plane in general, and which means that is out of plane warping that we're talking about. And within its own plane also it basically can change. So that's basically W2 and W3 components. So that's also taken into account in going from the orange to the blue. So that's basically your U. Next, in the deformed configuration here, we said that basically it can move to an intermediate state. that motion is basically accounted for by this u, which basically is that same material point on the reference curve here, which is small r, which has now changed to this reference curve capital R. So the intersection of the reference curve and the reference cross section in the deformed state is basically this point, and the position vector from its initial location to final location is basically denoted by small q. Now again, you can draw position vectors from the same point in the same reference frame A to the deformed configuration reference curve, which basically we call as capital R, and to that same arbitrary material point which was here and which has now come here on the blue surface, we denote it by R hat, and both these being uppercase to conform with our convention that we are dealing with the deformed state. Now, in addition to this rigid body like translations u, it can have rigid body like rotations, because of which your small b1, b2, b3 has now become big b1, b2 and b3. So there is a rotation associated with the cross section, because of which you now have b1, b2, b3 like this. But now you see that whereas b2 and b3, just like this small b2 and b3 will be on the cross section, the b1, just as here, will remain perpendicular to that reference cross section, which is basically that orange, but it need not in general be tangential to the reference curve R. Here it was introduced as being tangential to the reference curve R, but each cross section at different locations x1 can rotate by different amounts, and so it's possible that the B1 is no longer tangential to the new reference curve, and it is this difference between a tangent and the actual B1 which is actually the what is called in the common literature as transverse shear. So transverse shear is basically the difference between the rotation of your reference cross section and the cross section which remains normal to the reference plane. So for example, in Euler-Bernoulli beam theory, or what is commonly known as the engineering beam theory, that angle would be assumed to be 0. In other words, your capital B1 will be assumed to be tangential. Whereas in the Timoshenko beam theory, you will not do that, and you will allow for different angles for both of these. Now, it is possible that the beam itself at the reference curve level has either extended or contracted as a whole, or at individual locations, at individual stretches in between, because of which we no longer deal with a coordinate x1, but we deal with an arc length s, small s, basically along this particular thing. So this is an exception. We don't use capital S here. We refer to this arc length as lowercase s. So it basically runs from 0 again, but need not be till L. It can be some new length that the beam has acquired. Even if it is the same length, then individual portions at some locations might have extended and some others might have contracted to compensate each other. So all of that can be accounted for as well. Now let's go in detail once again to be more specific of what I have stated already. First of all, the small b1, the way it is introduced is you identify the reference curve and then you introduce a tangent to it, and as I said, because of the initial curvature, it can be a function of x1. Next, b2 and b3 are tangent to the coordinate curves x2 and x3, so you have cross-sectional coordinates x2 along b2 and x3 along b3. So a different way of saying is that you introduce the cross-sectional coordinates x2 and x3 and basically draw tangents to that, and that's basically your unit vectors b2 and b3. So that's basically what that states. And so in general, they can be functions of x1 as well, because even if you don't have initial curvature, for example, if you have just initial twist, you have b1 as a constant along the length, but b2 and b3 can change along the length because of the initial twist. So in general, b2 and b3 are also functions of x1, but none of them are functions of the cross-sectional coordinates x2, x3, etc. They are all functions only of the beam reference curve coordinate x1. Yes.
So when B1, B2 are function of x1, then B3 already is fixed.
That's correct. B1 cross B2 is B3. So basically, if you know B1 and B2, your B3 is fixed.
B3 we can't say is a function of x1.
Because B1 and B2 are functions of x1, so therefore B3 will also be a function of x1.
So
it's not independent in the sense that once you know B1 and B2, you know B3. First of all, its magnitude is known because it's a unit vector, and then it is also supposed to be mutually perpendicular to both B1 and B2 in such a way that it has to follow a textual triad. So therefore, its direction is fixed as well. So its magnitude and direction is fixed, so the vector is fixed. This particular reference curve, it is the same material point. See, first of all, you define this according to your convenience, whether there's local centroids or whatever. The same points have moved to a different location. So you draw a one-on-one mapping from the undeformed reference curve to where it is at a particular instant of time, and then you basically generate this curve. So because this particular point is common to the reference curve as well as the reference cross section, it remains the same intersection over here as well.
And it may not be a smooth
in general, it need not be. Yeah, that's it. Any other questions on this so far? So that's R we know. So now R hat is basically the position vector from a point fixed in the reference frame A to any arbitrary material point on the undeformed cross section. So that's given by this vector R plus a vector from this point, which is the intersection point, to the arbitrary material point. So obviously, because x2 is along B2 and x3 is along B3, so all that you have to do is to add x to B2 and x3 B3 to R to get the position vector of an arbitrary material point. Next, going from the green to the blue involves these three items, but going from the green to the orange involves just the first two items in this. So you have a rigid body translation u of x1, as I said, which basically defines your capital R. So that's basically u of x1 from R to R. So you see that there are two ways you can define this reference curve. Going back to your question, all the material points on this basically coming here. So that's one way of looking at it. The other way of looking at it is basically the origin of that cross section, where it has moved the loci of that. So it's two equivalent ways of saying the same thing. So basically, that's what this says. A rigid body translation u of x1 from R to capital R. Next is the rigid body rotation, which is from the small b system, which is fixed to that, now to the big B system, which is fixed to your orange thing here. So that now we can introduce a matrix of direction cosines C subscript ij, which is given by big Bi dotted with the small bj. Okay, so I and j, of course, taking all the values 1, 2, 3. So you have a matrix there. And because of the commutative relation, of course, you have a symmetric matrix as all direction cosine matrices are. So you have Bi dot Bj there. Next, an elastic warping deformation, which is what distinguishes the orange plane from the blue surface, which is the final surface. So the orange thing, remember, is not a reality. It is just for our own imagination of what is happening, we are introducing that. So all of these things, in other words, happen simultaneously. So just for the description's sake, we say that the green moves to the orange and then becomes the blue. But in reality, all of this happens simultaneously. So the difference between the blue and the orange is the elastic warping deformation, a three-dimensional field. So it has components W1, W2 and W3, generically referred to as Wi, along the corresponding unit vectors big Bi. So W1 is along B1, W2 and W3 are along B2 and B3 respectively. So W1 is what you typically see in a lot of textbooks, and then there is section of torsion. When you have a non-circular cross section for a shaft and you apply a torque to it, the cross section no longer remains plane, it warps, they say. So that warping is just W1, whereas when we say warping, we refer to not only that W1 but also W2 and W3. And W2 and W3 are also very commonly known even for example in isotropic beams because of the Poisson's effect. It's just an extension force results in a contraction along both the B2 and B3 directions. So that's the simplest example of W2 and W3. But these things become more and more complicated when you go to thin-walled sections, especially thin-walled open sections, where you can have much more complex warpings even for isotropic beams. And then when you introduce the further complication of anisotropy because of the composite materials, then it is definitely not trivial. Many of these things are fairly complex, but mathematically we have formulated in such a way that it is practical. Next. I mentioned this, so instead of x1 we now have s, but s is a function of x1. So in the simplest case, s will be of course equal to x1, but in general it's a function of x1. So this is the arc length along the deformed reference curve capital R. Next, we introduce v1. When we introduce small v1, remember we introduced it as tangent to R, but here we are not introducing it that way. We are introducing it as v2 cross v3. In general, it is not tangent. The whole B system is defined together as what has happened to small v, v1, v2, v3 because of the rigid body-like rotations of the cross sections. That's how all three of them are defined. So in other words, they remain mutually perpendicular to each other. They remain a dextral triad as well. Next, now we know capital R basically is a vector which defines points on the reference curve R. When we write these things on the, basically for illustration here we'll be using bold, but when you actually write down, you typically use an underscore to refer to all the vectors. Similarly, we'll introduce dyadics, which are the second order tensors. We'll basically use double underline, which is a standard notation in most references. So here you have vector r hat, which is the position vector in the deformed configuration of an arbitrary material point. Once again, I wish to emphasize that this is not necessarily on the periphery, that is on the boundary, but it can be anywhere in the interior as well, at some point, including possibly this point itself. So basically, all points on the cross section. So that r hat is basically what defines the blue surface over here. That is after the rigid body translations, rigid body rotations, and the warping. Whatever has happened is basically what is denoted by r hat. Now this r hat is again defined in a very, derived in a very similar fashion to the way we derived the small r hat, which is basically saying that we know the intersection of the reference curve with the reference cross section, and then we move on the cross section. So same thing is done here. Now suppose this term were not there, then the first three terms basically refer to the orange plane that you have there, that is the intermediate reference. In other words, you have that point which is the intersection of the reference curve and the reference cross section having moved here. So that's basically your capital R, which of course in turn is equal to nothing but small r plus u. So basically this position vector, initial position vector plus u will give you capital R. So that is basically the first term. Having identified that point, now you are basically saying that you have again on the cross section x2 and x3 are the coordinates, and they are now, instead of running on small b2 and small b3, are running along big B2 and big B3, because that's what has happened to small b2 and b3. Because of the rigid body rotations, they have become big B2 and B3. So this first three terms together basically refer to the orange plane. Now to that, going from the orange plane to the blue surface, we now add WI, which we basically introduced here, the elastic warping deformation. So now that basically accounts for the entire thing. Now, if you see, for any arbitrary material point, so you have a beam, you have a cross section, consider some arbitrary material point there. Now you have gone from that arbitrary material point has gone from the undeformed configuration to the deformed configuration. If you are only tracking that particular point, all you need is just three variables. Just basically From this location, it has moved to that location. So you need a position vector which will have 3 spatial components. So, for example, if you have the unit vectors A1, A2, A3 associated with the reference frame A, so you basically can have those 3 along the A1, A2 and A3, what is the motion that that particular point has had. But instead of just those 3 variables, we have now introduced actually 9 variables. The first set is of course contained within R because of this U, because U is a vector, remember, it has components U1, U2, U3. So that is the first set, and which defines the rigid body translation. Next is the rigid body rotation. From this green to the orange, it has rotated. So, and again, it can rotate about 3 different axes. There are many ways of representing the rotation, so we'll come to that a little later, Euler representation or Rodriguez parameters and so on and so forth. But whatever it is, basically it has undergone 3 rotations. So, in addition to the 3 translations, scalar-wise, we are talking about scalar component-wise, 3 translations, we have 3 rotations. So, 3 plus 3 adds to 6. And finally, in addition to the orange thing, now we have come to the blue by means of this Wi. So again, you have 3 components of warping, W1, W2, W3. So in other words, you have U1, U2, U3, you have theta 1, theta 2, theta 3, which define how big B is different from small b. And then you have W1, W2, W3. So total of 9 quantities instead of just 3 quantities that you had, which is basically one arbitrary material point moving from an undeformed state to the deformed state. So in other words, you have introduced 6 orders of redundancy, and that has to be accounted for, and we will see how that is accounted for as we proceed. Any questions on this so far?
This capital B2 and capital B3 in effect have 3 parameters, because theta 1, theta 2 and theta 3 will decide both of them.
Exactly.
In general they are vectors, but only 3 parameters.
That's correct. And once B2 and B3 are fixed, you know that B1 is fixed, because B1 is equal to B2 cross B3, so you don't need any additional information to fix that. Anything else?
So here warping W2 and W3,
Yeah.
they take care of the Poisson's vectors.
Yes, that is correct.
Can I say like this?
Yeah. They do.
So
So
material.
remember that functions of all 3 spatial coordinates. They are functions of x1, x2 and x3. Okay. So basically at different locations on the cross section, this is the cross section, at different locations on the cross section, W2 can have different values. For example, at this end it can have a different value, and this end it has a different value. So a contraction like this would basically mean that here W2 is positive. Suppose this is the positive direction of B2 here, and I am applying a tensile load to this, and it has a positive Poisson's ratio of this particular material. Then basically it's going to contract, which basically means that this particular point is going to move here, and this particular point is going to move here. So you have different values for W2, and that's basically what is taking care of that. But in reality, all of these, remember, are point features. So it's actually the derivative of W2 with respect to X2, which basically accounts for an addition to the strain in the 2-2 direction. And basically that in turn is related to the sigma 1 that you're applying, or epsilon 1 that you're applying in the longitudinal direction along the beam through the Poisson's ratio for an isotropic beam. Right?
So in this SWAM procedure, only these 3 warping deformations are introduced in this. When compared to any other generalized beam theory,
no. See, this is just a preliminary to the WAM procedure.
no, in this components,
Yeah.
9 components.
Yeah.
In generalized beam theory, you will have the other 6 components.
See, any other theory, for example, let's say the Euler-Bernoulli beam theory, will say plane section remains plane. So it's basically saying that all these warping are not there. So that will be a difference. But other beam theories can introduce the warping, but then as we are saying it is an arbitrary function of x1, x2, x3, and we want to determine how it is a function of x1, x2, x3. Somebody might say W1 is, let's say, varying in a particular way with respect to x2 and x3. For example, it's a constant. Or W2 and W3 are, say, linear in x2 and x3. In a thin walled beam with x3 along the thickness coordinate, they might assume that it doesn't depend on x3, or at the most it is linear. Some higher order deformation theories might assume it is quadratic or cubic in the cross-sectional coordinates, and so on and so forth. But basically, the primary difference comes in as not assuming anything about it. Again, in terms of the rigid body translations and rotations, we are basically saying that even that can be arbitrary, and they can be arbitrarily large as well. Okay, so some theories will basically impose a restriction on how large they can be, or which of those need to be accounted for a particular specific problem, and which can be ignored to simplify the derivation and so on and so forth. So here, when we are talking about beams, we are talking about not only bending structures, we are talking of axial loads, torques, and the bending moments. Any of these things, combinations coming from loads which are concentrated and or distributed, elastic foundations, again in terms of the boundary conditions, arbitrary. We are allowing for everything to be arbitrary, again within the cross section, the material distribution, etc., and the geometry of the reference curve. So all of this means that we cannot make any assumptions regarding this. We are developing a generic model which is supposed to be valid for any combinations of the loading conditions, geometry, and or material distributions. So keeping that in mind, it is a more general thing. But as I said, we have not yet applied the variation asymptotic method. We are only creating a geometrically exact kinematics, keeping it in place. When we apply the variation asymptotic method, we basically will bring this kinematics and introduce it there. For example, to define the strain, we will use this position vector. So using this position vector, we'll define the three-dimensional strains, and then that three-dimensional strain will go into three-dimensional constitutive law, which again will be a fully populated matrix, which means that we allow for all kinds of couplings. And if it's a nonlinear material, those matrix constituents cannot be constants. They can be functions of the three-dimensional strains itself. So then, once the geometrically exact kinematics is combined with the appropriate 3D constitutive law, which is typically obtained experimentally, then basically the dimensional reduction automatically happens when we apply the variation asymptotic method. Because of the geometrical exactness of the kinematics and the appropriateness of the constitutive law, you end up with a more reliable theory. Everybody else also wants to do that dimensional reduction because they want a computationally efficient model. They know they can't do over and over the 3D finite element analysis, for example, whatever the computational power they might have access to, especially for real-time problems and for detailed design optimizations, studies, and so on and so forth. So keeping that in mind, so basically what we are saying is that we also do a dimensional reduction, but the way we do the dimensional reduction, we do it in an asymptotically correct manner. So of course you get the computational efficiency which everybody else gets, but we are also getting the accuracy in the sense that it is almost matching the 3D results. If you had an elasticity solution, you would asymptotically approach that. In many problems you may not have an elasticity solution, you might apply a 3D finite element analysis and you see that it asymptotically approaches that. So when you say asymptotically, again the question boils down to how small is the small parameters that you have taken into account. So because it's a well-defined beam problem, so obviously the cross-sectional dimensions are small compared to the length, so it is a small parameter. Otherwise, anyway beam model will not be applicable. Leave alone our model, no model can be developed which will be applicable for a brick. If you want to model it as a beam, then obviously you're going to have huge errors. So in the kinematics, yes, one of the primary differences is in whether you take into account WI or not, and if you take into account, are you taking it as generic functions of x1, x2, x3, or are you taking it as some specific linear function? Most works will, for example, ignore W2, W3 and take only W1. And even if they take all W1, W2, W3, they might take it arbitrarily with respect to x1, but with respect to x2 and x3, which are the smaller dimensions for the beam, in other words, the breadth and the thickness are smaller compared to the overall length. So in those dimensions, they will say it explicitly depends on x2 and x3 in a particular fashion. There are yet some other theories which may take all of these three dependencies arbitrarily, but instead make the assumptions elsewhere. For example, they might assume the stresses vary in a particular way with respect to x2, x3. So we don't need to do that either. So that's basically the idea.
So we are solving for capital R hat, is that correct?
Right.
And our problem is because r hat happens to be a 3-dimensional vector, so our problem is 4-dimension because there's a parameter of length plus these 3. So, am I taking
No, see, the dependency on x1 is already embedded in this. So the r hat is a function not only of x2 and x3 but also x1.
But for each x, I'll have a different capital R. For each place in the beam, I'll solve it and I'll get 3 components of capital R.
No, in the sense that numerically yes, but in the functional form, the way we have defined, it is the same. The reason why R hat would differ from one to the other is either because of the rigid body motions or the different warpings of different cross sections. Now, all of that is already accounted for here, so you don't need to explicitly go and account for that. Okay. In a way, what you're saying will become visible. For example, when we apply the variation asymptotic method, the problem will automatically divide into 2 parts. Okay, one is the cross-section analysis, and the other is the 1D analysis along the reference curve. Okay, so in other words, you will not be solving for this r hat with respect to x1, x2 and x3, all 3 simultaneously. You will be able to solve with respect to x2 and x3 first, and then you will be able to solve with respect to x1. Okay, but all of that information is already embedded into it. You don't need to revisit the kinematics to do that.
Sir, if I say that this model is applicable, just one asking, this model is applicable for plate also.
Yes.
What is the beam
Similar procedure, not the same model, but yeah, similar
the
procedure.
beam R vector and capital R vector you write for any general structure. And the question is, what is the beam element in this? How does it differ?
See, by element, we are not already any way discretizing this. See, this need not go for a finite element analysis. Even a closed form analytical solution could still be possible with it. So basically, the way we distinguish a beam problem from the plate or shell problem is not in the way we apply the procedure, but in terms of how we basically separate out r hat. So here, in the beam problem, the way we have separated it out, the kinematics, is by saying that the total motion of an arbitrary material point is made out of 2 parts. One is the rigid body motion of the cross section to which it belongs, and then the warping. So in the case of a plate, what I will do is I take this plate, I take a normal to this. I basically say that now I want to know the motion of an arbitrary material point on this plate, which is a tabletop. So I select that arbitrary material point. I draw a normal through the reference curve there, to which it is a part. And now I track the motion of that particular normal. Again, remember, this is imaginary. It's as much imaginary as your orange plane over here. So instead of that orange plane, I now have a orange line. So this orange line moves like a rigid body. In other words, it has 3 translations and then it has 3 rotations. Of course, this particular rotation is called the drilling rotation. Sometimes you may need to account for it, sometimes you may not, because it's a line which is rotating about its own axis. Forget that complication for an instant, because we're just looking at the difference between beam and plate. Now, you have 3 translations and 3 rotations. Over and above that, there is warping. Here we define warping as how the orange surface changed to orange plane changed to the blue surface. Here we will define it as how this orange line will change to a blue curve. So in other words, this straight line can first of all change in its length. Okay, it can increase or decrease, and by different amounts at different locations. In addition to that, so that is basically if we introduce coordinates, let's say x3 along the thickness, so we are talking about a warping W3, which basically accounts for that. In addition, you will have W1 and W2, which will basically make, because they are different at different locations, they will make this straight line now appear like some arbitrary curve. Again, the way our plate theory or shell theory differs from anybody else's plate or shell theory is how you basically, one of the major differences is how you basically account for that warping. Some people might say, for example, this W1 and W2 are constant or they are linear with respect to X3. So based on that, all the derivation, for example, the Kirchhoff-Lau hypothesis. The Kirchhoff-Lau hypothesis states that the three-dimensional strain is linear in the thickness coordinate. Because it states that an inherent assumption is made about the displacements, because the strain is defined in terms of displacement. If the strain is linear in X3, you can say what the displacement is in terms of X3. So in other words, without even solving for it, you are already assuming how it varies with respect to X3. There only X3 is involved because X3 is the smaller of the three coordinates in terms of dimensions of the overall structure. So thickness is small compared to the length or width of the plate. So that's basically why. So whereas we take an arbitrary W1, W2, W3 there as well. But in terms of how you actually put this, it might look very similar, but there is a difference in the interpretation for this part. Here it is what has happened to the green coming to the blue plane. There it will be what has happened to the green line, how it has become the orange line. And here this basically refers to how it goes from the orange plane to the blue surface. There instead we will be talking how the orange line became a blue curve.
Also, will we be considering the reference surface rather than the reference line over there?
Yes,
in terms of R and R.
Exactly. So it's the next level. So we're basically the problem splits in the main case into two parts, which is 2D first, which is the cross-section analysis, and then the 1D, which is the reference curve analysis. Exactly the opposite happens there. So what Keshav points out is basically that here one part, the first part that you're going to deal with now is 1D, which is basically the analysis of the normal. And what was originally a normal need not be normal to the new reference curve surface. And in addition, you have the 2D reference surface which has now deformed, and you have to analyze that, for which the inputs of this 1D analysis will be used. It's exactly opposite here. You do the 2D cross-section analysis and the inputs goes to 1D. So here it is first 2D and then 1D. There it is first 1D and then 2D, which is the reference curve, reference surface analysis instead of the reference curve analysis. Any other questions? Next, we have been doing this classification of 4 different types of variables which define the mechanical state of any structure, be it a beam or plate, shell, or even arbitrary three-dimensional structures which need not be either a beam or a plate or shell. So in all such cases, we have loads, that basically the yellow quantities here, the stresses, the strains, and the deformation. We start with a three-dimensional model and then eventually we go to a dimensionally reduced model. Now basically the relationship between the load and the stress is an equilibrium equation, because now we're talking about both 3D quantities. The equilibrium equations are also 3D. Similarly, 3D stress to 3D strain is the 3D constitutive law, and then again the relationship between 3D strains and 3D deformation is given by the 3D kinematics. So everything basically fits snugly into this. So let's illustrate this. First, for example, the 3D loads could be tractions, TJ, which are basically applied. So you take an arbitrary three-dimensional surface, something like this, which in a special case could be a beam, for example, or a plate or a shell. Now you have, at some locations, you have, let's say, a distributed force. At some point, you could apply some kind of a torque or a couple. Some location, you could apply, let's say, concentrated load, and in some other locations, you could have some boundaries. You define basically the deformation there, either that the displacement is 0 and or the rotations in particular directions are 0. So this is an arbitrary way of posing a three-dimensional problem. So in such a situation, all these quantities that we have indicated here in this particular example is basically what fits into the 3D loads. Now these are what we call as the tractions Tj. In addition, you could have body forces. For example, due to the self weight of this, the gravitational force is a body force. There could be many others as well. But you can have those body forces as well because they can cause deformations, as you very well know. So body force per unit mass will represent it as B, flowery B with the subscript J over there. Next, the 3D stresses, which are basically your sigma ij, and then the 3D strains will represent it as capital gamma subscript KL, and this is the notation we will use throughout the course. Even when we go to beams, we will refer to 3D stresses as sigma and 3D strains as capital gamma, and we'll use different notations to distinguish. Okay, this one. Yeah. This particular thing over here, you see, is the way we introduce the 1D strains. Actually, there are further terms which are missing here. It's okay. R prime is equal to 1 plus gamma 1 1 along B1 plus 2 gamma 1 2 along B2 plus 2 small gamma 1 3 along the vector B3. Okay, the second line is okay. There are no addition terms here. There are some terms missing because of the aspect ratio problems. But basically, you see that prime is a notation we will use to denote partial derivative with respect to x1 throughout the course. So basically, remember that this capital R is actually the reference curve's position vector from the same point in the reference frame A. So now how that varies with respect to x1 is basically like this. It will have a B1 component, a B2 component and a B3 component. Suppose you are talking of very thin and slender beams, very long basically, then that's what it means. Suppose in other words transverse shear is not there, then these two terms will not be there. So you can very easily see what is basically happening here. R prime would be B1. In other words, what we showed B1 here is not tangential with respect to the reference curve, can actually be tangential under the condition that gamma 1 2 and gamma 1 3 are 0. So in other words, the only difference between B1 and a tangent unit vector to this is basically 2 gamma 1 2 and 2 gamma 1 3. The next aspect is that the tangent, for example in this case, R prime itself is defined as B1. So in other words, it is a unit vector as well. But here, even if the transverse shear was 0, in other words, B1 is tangential to this, still, if you take capital R prime, that is derivative of R with respect to x1, then you will not get a unit vector. Because now remember the arc length is S. On the other hand, if you take the derivative of this vector R with respect to S, then you will get a unit vector. But here, you are taking derivative with respect to x1. So basically, it is the extensional strain gamma 1 1, and all these small gammas are functions only of x1 by definition. So what we are saying is they are 1D strains. So gamma 1 1 is gamma 1 1 of x1. Similarly, your transverse shear strains are also functions only of x1. So we call these as 1D strains. These are not all the 1D strains. We'll come to the others shortly. So the reason why we call them as one-dimensional strains is because they are functions only of x1. They are basically referring to what is happening to the reference curve from its undeformed configuration to the deformed configuration. One is because of the extensions, the other is because of the transverse shear. So the extensions is what makes the original unit vector, in other words, your vector R, if you take a prime, that is basically partial derivative with respect to x1, that was just B1. In fact, that's how we define B1. Okay, we define B1 as a tangent unit vector to R prime. So that's basically what it was. Now you see that B1 has become big B1 and it's no longer a unit vector because of the extension or contraction which is accounted for by this extensional strain gamma 1. In addition, in general problem where the beam either may not be slender or the material which is used for making the beam has a low shear modulus, then in particular directions, then you can have these effects as well, 2 gamma 1 2 and 2 gamma 1 3. Next, we introduce further one-dimensional strains. Now you see that the partial derivative of big Bi with respect to x1 is written as vector k crossed with the same vector Bi. Again, in all of this, the Greek alphabet, whenever we use, as I already mentioned in the previous class, will take on the values 2 and 3, and the Latin indices will take on the values 1, 2 and 3, and we'll also follow the notation that if the index is repeated, then there is an implied summation as well over the entire range. So in this case, the repeated index is I, the subscripts here and here are both I, which basically means that there is a summation over I equal to 1 to 3. For example, if alpha is repeated, then basically it means that there is a summation from alpha equal to 2 to 3. Now here, there is a big K here to distinguish from a small k which we will use in the undeformed state. Remember, we are using lower case for the undeformed state and upper case for the deformed state. So same thing holds for k as well. So we will introduce, for example, we said that the Bi in general are also functions of x1. So they will have a derivative with respect to x1. So in this case, it's not a partial derivative. So in this case also it's not a partial derivative because these are functions only of x1. So it is a derivative with respect to x1 because that's the only thing they depend upon. Unless of course you're talking of a dynamics problem, in which case it depends on time as well. So it's probably more appropriate to call it as partial derivative here in general because we will apply these things to dynamics as well. But here it is the undeformed state. So here it depends only on x1. So it's actually a derivative, not a partial derivative. Now this will be small k vector crossed with small vi. So basically how a unit vector changes with respect to x1 will depend on the initial twist and curvature. You can check this for simple examples. Take one at a time because this k, remember, is equal to ki bi. In other words, k1 b1 plus k2 b2 plus k3 b3. You take one at a time. Let's say k1 small k subscript 1 is nothing but pre-twist, initial twist. So if you take k1 alone, you will see what is the effect, what will be b1 prime, b2 prime, b3 prime. You will see that b1 prime, for example, is 0. In other words, b1 doesn't change with x1 if you have only twist. Similarly, you can take one at a time the curvature, let's say k2, and keep k1 and k3 0. Then you basically see what will happen. You can understand the geometric aspects there. So whatever we have at the undeformed configuration, we have a similar analogy at the deformed configuration level because that's how the big B's change. But now instead of the initial twist, we have the total twist and curvature that we have here. Instead of initial twist and curvature, we have total twist and curvature, which basically accounts for the initial twist and curvature plus whatever additional twisting and bending has happened due to the applied loads, which are basically over here. So I think on this we will stop today's class. In the next class we will start with that three-dimensional relationship between that, and we will see what happens when we reduce it to one dimension. What is the summary of the results? That is, even before we apply RAM and get the results, I will this was supposed to be a preview, but it's just half a preview today. So the remaining will do in the next class, and basically there we will illustrate how that relationship between load, stress, strain and deformation in 3D gets transformed into 1D, and that dependence that we're talking about purely on material, purely on geometry, purely on conservation laws, etc., how it gets hazy when we do the dimensional reduction, how the information flows from one aspect of the problem definition to another.